Hey there YouTube, FNR Racing here. Today I've got a special treat for you because I pulled the front shocks off the car. And as you can see, it's not supposed to do that. And if you can probably see the little hops it's making, as they say in La Belle Province, ça c'est tout fucké. So what we're going to do today is we're going to see if we can't get this thing apart and figure out how the electronic suspension feature on the Stealth actually works. So this here is the underside of the shock tower cover. This blister, this plastic thing, is the reason why the Dodge Stealth has those two bumps on the hood. It's clearance to make room for this. This is the connector that goes to the ECU that controls the shocks. And this wire comes in here and it plugs into the top of the shock using this connector here. And there are 5 wires in here that plug into a receptacle at the top of the shock rod that go into the shock and do something interesting. This electronic suspension is seriously crude. What it does is, based on a couple of inputs that the computer has, it tries to predict what the car is about to do dynamically, and then it can change the damping inside the shock by revalving the shock on the fly. This is equivalent to getting a Coney Yellow or a Penske that has a rebound adjuster on it and having a motor that twists it to a certain setting based on what the car is about to do. The idea is that you can leave the shocks in full soft when you're just driving around and being a dude, but as soon as you do anything spirited, the car can then crank up the shocks to provide better dynamic handling and faster transient response. It's a really, really ugly hack, but it works. And if it's stupid and it works, well, then it ain't stupid. So the next step is to try and get the shock apart and see what these wires hook up to and how the mechanism inside the shock works. So here's our first obstacle. This is a dust cap that appears to have been press fit down over top of the shock. And that means we got to be able to pull this off somehow. You probably whack it with a hammer and a drift and see if that works, but there's a better way to do that. Now what I'll do is I'll go ahead and make myself a puller and use that to pop it off. So I've gone ahead and blacksmithed myself together a puller. Pretty simple design. This top plate fits down over top of the shock shaft. This U-shaped section fits underneath that dust cap, and by tightening down on these 2 bolts, you pull the thing up and that pops the cap off. I'm not going to show you how I put this thing together. I didn't bother filming it, because if there was a real machinist watching me put this together using my first generation Chinese 3-in-1 machine, it'd probably give him a serious case of the heebie-jeebies, because it was ugly. If you really want to know how it went, annular cutter to cut the initial hole, boring bar to take this out to size, corncob roughing end mill to cut the slot here and here to take out the center section and true it up a little bit, and that side is just drilled. And these 2 holes here are tapped for the M8 bolts that I've got thrown inside there. That's really all there is to it. Not exactly rocket science. So here's the top seal puller in place. You can see it's worked as designed. We can go ahead and pull that right off. And look at that. They've crimped the top seal in place using some sort of press. And underneath there, that's the seal with the wiper for the shaft right there. So in order to get this apart, I'm going to have to pry these crimps open. Now normally, this shock is pressurized with nitrogen to prevent the oil inside from cavitating and the shock strokes really fast. This one has been leaking and it's lost all its nitrogen pressure, so I should be able to pull these things open without worrying about it blowing up in my face. Let's find out. You know, the first time I ever opened up a shock, I blew the shock rod across the side of my apartment and embedded the shock rod in the wall across the hallway. See if I've learned anything since then. Well, there you go. That's the seal. Pretty robust. And we've got okay, it's going to be a little more clear and sounding. All right, so there we go. And it is a twin tube like a Coney. We'll just work some of the oil out of it. So there. That's the inner tube. Right there, of a twin tube shock. The shock body is full of oil, as it's supposed to be. And here is some of the valving down here on the bottom. Let me just get this all cleaned up. Let's have a look and see how it works. So this is the foot valve. Should just unscrew. Yeah, there goes a bunch of rattling inside. So there's a shim stack on the bottom. Very similar to how a Bilstein goes together, same idea. But it's on the foot. Yeah, I popped the shim stack loose on the other side. That's not how that comes out. Okay. So that's how it's valved. That's not how it comes apart. So that's the outer tube of the twin tube shock. That there is the foot valve holder where the foot valve stack goes. And that was just pressed inside. And I thought it might have been threaded, but I twisted it and it wouldn't come off. And finally I just gave it a yank and pop, out it came. So that's where that goes. And the valve stack for the shim stacks just bolt onto that with using a nut. Right there. So that would actually be assembled as one unit and then pressed on at the end. Up on this end, nice phosphor bronze bearing in there, nice and solid. And a seal here, which I started taking apart because I thought this might have unscrewed too, and it might yet. But there, we got it apart. So that is the meat of the operation right there. We've got a nut here and a preload spring. This is the main piston. And another nut here, and there's a low speed passage on that, which is a bypass. So here and here. So it looks like my next step is going to be to take this nut off and screw that off. That's threaded there. Still no indication where the electronics are though. Up to this point, it looks like a normal twin tube shock. There's nothing that would give away the fact that this is full of all kinds of electronic gadgetry. Interesting. And this, with the main shock shaft, you see in there. So that's the motor housing. That little tang inside is the end of the motor, and those three tiny Phillips screws, little watch screws, are what's holding the motor inside. The rest of this shaft is all one machine piece, with the exception of the end cap up in here where the wires are. Right in there. And it's got some heft in it because it's got a motor inside. So the next step is going to be trying to pull out those three Phillips screws without stripping them and see if I can get the motor to come loose. So this is the bypass spool valve. Oil comes in and out of this part here, flows through the hollow section of this, flows up through the hollow section of the rotor, this part in here, and goes out a set of orifices here, and there's another pair on the other side, over here. By the rotor rotating in its space here, using this tang, using the tang that engages with the motor drive, it exposes a series of orifices. There's a small one like that, and there's a large one. And they correspond to the same orifices on the other side. So when you're on large on both sides. So as this rotates, you go large orifice, no orifice, small orifice, no orifice, large orifice. The larger the orifice, the more oil goes through. The more oil that bypasses the piston head, the less low-speed force it makes, because it's the restriction that causes the force. So what this means is that as the motor rotates, you get full soft, full hard, medium, full hard, full soft, full hard, medium, and so on and so forth. So here I've just gone ahead and fitted the piston on so you can see how the bypass mechanically works. This is the piston that normally produces the majority of the valving. The slots in the end of it and the shim stacks, little stacks of spacers like this, those determine the primary valving of the shock. By allowing oil to come in the base of this spool valve, flow through it, and come out of this orifice in here, that allows some of the oil to bypass the shock, and in so doing, change the force that the piston makes depending on how much oil is bypassing the shock. The more oil that goes past it, the less force the piston makes. So there you go. That's just how that fits on there. All right, quick recap. Here we have the shock shaft, inside of which is the motor that controls the bypass valve that controls the low-speed bleed shock damping force. This is the shock shaft, inside of which is the motor, and that motor controls this spool valve here, which is itself the low-speed bleed bypass that allows oil to get its way around the piston head, this thing right here. And by varying the amount of oil that can bypass the piston head, changes the shock force. What I've done is I've hooked up the wiring harness from the car. It turns out that I can't reach inside the shock. The pins are too small to be able to hook up any jumpers to them. So I've connected the OEM wiring harness to it to get access to this plug, because I have some spare pins for that makes it easier to hook up these jumper wires. And by going ahead and doing something unusual, which is reading the shop manual, I've been able to figure out that the first two pins on this harness control the motor. The interesting thing is what the other three pins do. Initially, I thought I was looking at a 5-wire stepper motor, and that's not what's going on. Instead, the last 3 pins are hooked up to a rotary switch array. And depending on the pattern of those switches going low and high, they are shorted out to each other depending on whether or not it's in soft, medium, or hard. So the way this whole thing works is the computer commands the motor to turn on, the motor rotates, and that switch array goes hard, soft, hard, medium, hard, soft, hard, medium, hard, soft, hard, medium, like that. And then the computer just shuts it off whenever it sees the switch pattern that it wants to see for whatever force it's trying to command. So what we're just going to demonstrate is I'm going to put that in there just to make it a little more obvious. And if I've got this whole thing hooked up right, turning on the power supply, I should make that rotate, and you see how it works. Shop manual said this thing uses 9 volts. It doesn't say what the amperage limit is, so I've set it at about half an amp. Yeah, there you go. So let's see what happens. There you go. You can see the motor rotating that rotor, and by doing so, changing the pattern of orifices that is exposed to the rest of the spool valve. That's really all there is to it. It's a really simple device. Let's turn that off. It's a real complex combination of super high tech, at least for the 1990s, and really basic stuff. This design with the rotating spool is both crude and smart. It's crude It's crude in that you can't command a valving function directly. You can't say, go directly to hard and snip, and it goes right there immediately. There's a little lag while the spool rotates over into the configuration that it wants. And I'm really very curious to how accurate it is to hit that. The timing between when the switch flips and when it shuts off and when this thing actually stops, or maybe some hysteresis in there. Future research, I guess. But it's smart in that it's really easy to do self-diagnostics, because if you want to see if the motor's working, you turn the motor on and you watch for the switches to change. And if the switches don't change, then either the harness is broken or the motor's not working. So it's really easy to build self-diagnostics into it. Whereas with a commanded one with no switch feedback, you just basically run the stepper motor and you have no idea of knowing if it made it or not, because there's nothing to tell you if it did. The quality of this, like the machining on these valves and the machining on here, it's spectacular. Like, it's an order of magnitude better than anything else I've seen in the car. It's very sort of Penske-esque. I really wonder who the OEM was for this. It might be Koni. It might be a Japanese manufacturer. I'd be very surprised if it's Mitsubishi in-house, just because it's so specialized. I don't know a whole lot about twin tubes. I spent my whole racing shock valving career doing monotubes, Penske's and Bilsteins mostly. So I can't really comment on the quality of the innards, but it looks very similar to the quality I expect out of a Bilstein or Penske. If you feel those parts in my hands and you said that that came out of a Penske, I'd have no reason to doubt you. That's really very, very nice. So there you have it for that. I tried getting those little screws inside out to expose the motor, and the tiny little Phillips screws that are in there have nothing of it. I think it made me Loctited in place, so in order to see that, I'm going to have to drill it out. But that should do it for now. And I like the fact that I can demonstrate how the motor works. My only regret is I wish I had an LED array so I could hook it up to the switches on here and show the lights flipping on and off as it went. But in order to do that, I have to delay the video to buy myself some LEDs. And Radio Shack doesn't sell that stuff anymore, so it means eBay or Amazon, and I'm not waiting for that. So there you go. That shows how the electronic suspension on the Dodge Stealth works. I hope you learned something. I certainly have. This has been fun. Thanks for watching. Stop it now. Woohoo, look at it go.